I have here the RISC-V instruction set manual, and I want to build a 32-bit RISC-V CPU. In here we have a number of different specifications. The one that I plan to implement is the RV32I, which is the 32-bit base integer instruction set. And if I look in here, I can find all of the instructions and exactly what they have to do. I thought I'd start with some of the arithmetic and logic functions. In particular, I think I'll do add and subtract to begin with. Now, previously I've built this 4-bit adder, and this works fine for 4 bits, but it does have a couple of problems. First of all, I want to build a 32-bit adder, and a 32-bit adder is going to be 8 times the size of this. This already has 5 ICs on it, so I'm going to need 40 chips like this, and that's starting to get a bit too big to be practical to build in this way. It also has another problem, which we'll have a look at if we look at the design of how this ripple carry adder works. We can see that the 4 bits that we have here and here, so we have 4 bits for A and 4 bits for B, they're spread out down the left-hand side here. Just looking at the A0 and B0 inputs here, we can see they go through the exclusive OR gate, and then they go through, and also the AND gate here, and they go through this AND gate and then this OR gate. So that we've got 3 layers of logic, and then we produce a carry. The carry is rippled into the next circuit, where it has to go through the AND and the OR of that one, ripple carry through, and so on. So at each stage, we're going through an AND and an OR, so we have 2 gates worth of delay. It takes time. There's a propagation delay as we go from the input to the output of every gate. So in order to calculate the carry out, the final carry out of this circuit, we have to go through these 8 layers plus the initial AND gate here, the XOR and the AND gate at this initial input. And so it's quite a few steps, and it's quite slow. If we want to build this for a 32-bit adder, then we're going to need 32 stages, and that's going to be 65 gates that the propagation of information has to flow through. And that's very slow. Even for the purposes that I have here, which is more for educational purposes, it's still very slow for our adder, and so I don't want to use just a 32-bit ripple carry adder. Instead, I'm going to use a 74HC283. And this is another 4-bit binary adder, but it comes in a single chip. So we have the integrated circuit here. So it's 1 chip instead of 5. It's still a 4 adder, but it has fast carry. And so it doesn't rely on a ripple carry mechanism in order to produce the carry out. If we look at the diagram here, we can see that in order to produce the carry out over here, it's actually using some combinational logic rather than relying on rippling through different stages. And so in fact, all of the bits, all of the 5 bits, the 4 bits of our sum output and the bit of our carry are all produced quite quickly. But we do still have a carry out, and so we can ripple a number of these together. So let's jump over to KiCad and we'll build that now. So we'll start by placing our 283, our 74283. And it looks like we've only got the LS model here, but the pin out is the same, so this will be fine for drawing our circuit. And we'll need 8 of these. Now this is already taking up quite a bit of space, so I'm going to hit S and create a subsheet. We'll call the sheet add32, because it's a 32-bit adder. In fact, I'll call it adder32. And then I will move these components inside of here. This way I can create a 32-bit adder here and use it inside of the other circuit without taking up too much space on the schematic. Since this is a subsheet, I'll need some hierarchical labels. So I'm going to place one for each of our 32-bit inputs. So A31 to 0. And using this square bracket notation, I'm saying that I actually have 32 bits here, and this is a 32-bit bus. I want it to be oriented so that it's on the left, and I'll connect that up here. I'll add another one here for B. And then we can add another one over here for our sum output. Select it as an output. Now I can wire these up to our A and B inputs on each of our 283 chips. And now we just have to do that for all of the other chips. Next, I need to wire up the carry-ins to the carry-outs. And I'll create hierarchical labels for the carry-in and carry-out. Now I've returned to the root level here and I'm going to import the sheet pins. This allows me to add the pins that I've just created in the subsheet, and I'm just putting them in here so that I can access them from the root level. Now that we have our 32-bit adder, we can wire this up as we see fit. But I want to optionally do subtract. So I'll have a subtract flag, and if subtract, then our operation here shouldn't be A plus B, but it should be A minus B. And otherwise, it should be A plus B. So we need to be able to negate B somehow. So we'll do A plus negative B. So how do we make negative B? Well, remember that negative B is actually equal to not B, or the inverted B, plus 1. Recall that this is how 2's complement represents a negative number. So we need somehow in our circuit to invert B and add 1. Well, the plus 1 is very easy because we can just add a 1 to our carry in here when subtract is true. So the next thing that we have to do is to invert B. So when sub is true, we invert B, otherwise we leave it alone. And we can do that with an exclusive OR. We can put B here and sub here, and then the output here will either be inverted or not, depending on sub. If you remember the truth table for the exclusive OR, so if we have sub and we have B, then sub exclusive OR B, if sub is 0, then we simply get B out because 0 exclusive OR 0 is 0 and 0 exclusive OR 1 is 1. If sub is 1, then we invert because 1 exclusive OR 0 is again 1 and 1 exclusive OR 1 is 0. So because of the truth table of the exclusive OR, we can see that by setting sub to 1, we invert. So I need to throw in 32 exclusive ORs into my circuit here. So these are actually all of the bits of B. These are 32 exclusive ORs, and then each one will have the sub input. So I'll create another sub module, and it will be a 32-bit exclusive OR array. So once again, I'll create a sub sheet. Let's put it over here to the left, and we will edit this sheet. The exclusive OR gate that I'm going to use for this is the 7.4 series, and it's the 86 chip. We can see that we have 4 exclusive ORs in here, so I'm going to need to add 8 of these. So I'll start by adding just 1, and I'll wire all of the gates up by adding labels. One of the labels simply indicates whether or not we are inverting, and that's going to be the same on all of our exclusive OR gates. While I'm here, I might as well add in our power, and then I can duplicate this 7 more times. And now the tedious task of labeling. If I add a label here and I call this A0, and give it the correct orientation and add it in. I have an option to hit either insert, or in my case I've got it connected to F1. It will add another label with the next number. So if I just keep hitting F1, I will keep getting the next number that I want. Although I do notice that it puts it in a different place than where I want it, so it's not entirely as convenient as I would like. Okay, I've got all the labels in there, a bit of a tedious task. What I ended up doing is I'd hit F1 in order to give me a label with the next number, and then I would hit M to move and then drag that into position. So now I need to have the inputs and the outputs, same as I did last time. So I can hit H for our hierarchical label, add our input, and then add our output. Actually, I accidentally set that as an output, so I'll change that to an input. And then I'll add the power and ground as well. So now I can return to the root page and add in our labels. Except I forgot one of the labels. I need to add in the direction, the invert or not invert. Now I can move our sub here and wire this into B. Now I realise I've forgotten to give power and ground to the adder, so I'll come in and wire that up now as well. Okay, and there's our circuit, and this should be able to add and subtract. We have our A input here, and our B input, which optionally gets inverted, and then we have subtract here to add 1 to turn our B into negative B. In either case, our sum or the subtract result comes out here, and we also have a carry output which we may or may not use later on in our circuit. Now the next step here would normally be to turn this into a PCB and print it, maybe add some LEDs and some toggle switches to give us input, and then we can test that it's working. But as I build the CPU, it's going to get more and more complex. So I want to test the logic of the circuit. So I'm going to leave this video here, and in the next video I'll implement this again, but using a hardware definition language. And I can use that language to simulate the circuit, and as the CPU grows bigger and bigger, that will become more and more useful in testing that the changes I've made haven't broken anything and that they do what they're supposed to do.